Hi, Assalamualaikum. So, we are from Group 2 and will be presenting about forward flats, especially on optimizing magnetic core material for transformer efficiency. But before that, let's meet our team. Okay guys, so this is our team. So we have Hakimi, Muhammad Ali Hakimi, Hakimi Zulkarnain, Wan Muhammad, and the last thing is me, Muhammad Hakim. So this is our project called Flex Forward Optimizing Magnetic Core Material for Transformer Efficiency. Okay guys, so in the table of content, we have introduction and background, objective, project scope, methodology overview, key finding, data and observation, analysis, and the last one is conclusion.
Alright, so this is our introduction and backgrounds. So first we have the performance of a transformer is highly improved by the magnetic core material. Second, the study emphasizes understanding material behavior and practical limitation rather than achieving full functional performance. Third, different core materials has highly different properties such as magnetic permeability, core loss, and saturation. The next one is transformer are widely used in electrical system for voltage, conversion, power transfer. This project focused on comparing different car material in a mini transformer using the same number of turns. And the last one is in practical application, transformer performance is often affected by non-ideal construction and loss. Objective. The first one is to study the effect of different core materials on transformer behavior. Second, to relate theoretical transformer concept with real-world implement challenges. Third, to identity factor contribution for non-ideal and non-functional transformer operation. Fourth, to observe practical limitation in mini transformer construction. And the last one is to compare transformer performance using the same number of turns for all models.
Our project scopes of these projects includes a basic study of magnetic flux and the role of magnetic cores in transformers, introduction and comparison of different magnetic core materials such as iron and ferrite. It is design of a laboratory scale transformers model for educational purpose only. Observation of magnetic flux behavior based on theoretical concepts, and analysis of factor affecting transformer efficiency through literature review and model observation. We have a few limitations for our project. The replica is not working and intended only for concept demonstration. We also have a limit in terms of time, cost, and laboratory equipment. For methodology overview, we construct mini transformers model, one core material per transformers. We selected different transformers core material such as ferrite, silicon steel, and powdered iron. We design transformers winding, the same number of turns for all model, and a same wire type and winding method. We also apply AC input voltage. It is for identical input conditions for all tests. Also, we observe transformers behavior for output response, heating and stability, and also magnetic coupling effectiveness.
Okay, now for key findings slide. First, we found that transformer performance is highly independent on the properties of the core material. Even when we use the same number of turns for all replica, each core show different magnetic behavior, such as influx flow and energy loss. Next, the replica help us identify several practical limitations, including flux leakage, core losses, winding alignment issues. This problem occurred due to imperfection in construction and material limitation. This experimental limitation clearly highlight the gap between theoretical transformer design and real-world implementation. Finally, our finding confirms that ferrite cores are more suitable for high-frequency application, while silicon steel core perform better at low frequency, which align with established transformers theory.
Okay, now is data and observation. As you can see, the data is compared for a different magnetic core material based on magnetic permeability, hysteresis loss, eddy current loss, and overall efficiency. This comparison help to identify which material provide better transformer performance. Even though we only made a replica, we can still compare how different core behave. So now is observation slide. From this slide, I will make a simple explanation from the data. So based on data, ferrite core show the best performance due to its low hysteresis and very low eddy current loss. Silicon steel also perform well because of its high malleability, making it suitable for power transformers. Powder iron core provide moderate efficiency as it reduces eddy current loss but still experience high loss compared to ferrite. So now is the analysis slide. So from the data, this analysis compared three types of magnetic core material used in transformers. That is powder iron core, silicon steel core, and ferrite core. Each material affect voltage output, heat generation, and efficiency differently. First, the powder iron core. The powder iron core produce a low secondary voltage. It also generate medium heat, which indicate high energy loss. This happen because its magnetic flux radiance is not very efficient. Therefore, it is suitable for high efficiency transformer application. Next, the silicon steel core. The silicon steel core is the high secondary voltage among the three. It generates low to medium bit, meaning energy loss are reduced. Because it is laminate, eddy current loss are minimized, making it the most efficient core in this comparison. This makes silicon steel ideal for power transformer and low frequency application. Finally, the ferrite core. The ferrite core produces a slightly lower voltage than silicon steel, but it generates very minimal heat. This shows that hysteresis and eddy current loss are very low. Ferrite core are best suited for high frequency application, offering moderate efficiency with excellent thermal performance.
In conclusion, since our product is only a replica and not fully working model, this experiment highlight the challenge and limitation involved in achieving optimal transformer efficiency using different magnetic core materials. Even though the transformer did not function as intended, the experiment still provide valuable insight into transformer design, core material selection, and the factors that affect core performance, such as flood leakage, core losses, and construction accuracy. Through this project, we gain a better understanding of how theoretical concepts differ from a real-world implementation, especially when dealing with practical constraints. Overall, this replica-based study helps us identify what adjustment and improvement are needed in future models to enhance efficiency, reliability, and overall functionality. This is our first replica, which uses a silicon iron core. Silicon iron is commonly used in power transformer that operate at low frequency, such as 50 to 60 Hz. When alternating current flow through the coil, it produces a changing magnetic field. The silicon iron core provides an easy path for magnetic flux, which helps strengthen the magnetic field. The core is originally made from thin laminate sheets to reduce energy losses caused by eddy currents, but we use tape and spray to make the replica look like the original silicon iron core. Even though our model is only a replica, this replica will help us understand how silicon iron core improve efficiency in real transformers. This is our second replica, which uses a ferrite core. Ferrite is made from iron oxide and ceramic materials, which make it electrically non-conductive. But to replicate it, we use tape, we use rope, and we also use old boxes. And how does it work? When current flow through the coil, a magnetic field is created and guided through the ferrite core. Because ferrite has a very high electrical resistance, eddy current losses are very low. This makes ferrite core suitable for high frequency applications such as phone chargers and power adapters. Although our model does not operate perfectly, this replica will show why ferrite is preferred at high frequency. This is our third and last replica, which uses a powder iron core. Powder iron core are originally made from iron powder mixed with an insulating binder, but we're using rope, tape, and toothpick to replicate it. How does it work? Each iron particle is electrically insulted, which helps reduce eddy current losses. When current flows through the coil, magnetic flux passes through small air gaps between the particles. These air gaps help prevent magnetic saturation. In conclusion, even though our model is only a replica, the three replicas successfully demonstrate the different characteristics and application of silicon iron, ferrite core, and powder iron core in real electrical systems.